So I'm going to talk a little bit about work I did a few years ago, analyzing lots of point data to help locate a new fire station. Um, and in this, it was a presentation. Now, I'll just kind of be talking about the work I did, but um, in this work, there's a lot of great examples on analyzing point data and visualizing spatial trends in the data using some more advanced techniques that we haven't gotten into in this class. And hopefully, you'll learn about in the future if you keep pursuing GIS. So, here it's, roughly 8 years worth of point data. And when you just look at the data, you can't really tell a whole lot from these points. So, what we try to do as GIS analysts or, public health GIS analysts is to tell a story with this data and to try and extract meaning from this data. So that's kind of what, I try to do here. And so the first thing that I wanted to do is use kernel density, which some of you touched on in your journal articles. And basically that's just creating this continuous surface of a visualization of where the most points are occurring. And that's, it's pretty easy to do using the kernel density tool if we were just to take all the years together. But if we want to look at how data changes over time, we need to consider our classification scheme. Because if you just did this, if you just did the kernel density for each year and you gave it its own classification scheme, you might have 2013 as one classification scheme, 2010 as another classification scheme, and you wouldn't be able to directly compare those years because each would have 10 classes. You'd apply the same color scheme, and you'd have this color red and this color red representing different color values. So each year would look just as bad, or the points would be just as dense as the previous year, 5 years prior. So what you need to do is really consider how you're going to apply data classification schemes across years if you really want to apply or compare data across years, if that's what you're trying to do with kernel density. So basically you need to take the classification scheme from the highest year with the most dense amount of points and apply it to every other year. And when you do that, we can take a look at the point density as we go throughout the years, right? So this is automatically playing, but we'll stop it so we can kind of go step by step. So you can see how these couple spots, or some people call them hot spots, I don't really like that term, but you can see how they emerge. And as we go back, we can directly compare between years, and especially if you watch down here, we can see how that was nothing, but it grows, right? You can see calls for service grow year over year because we're using a classification scheme that lets us compare year over year. We're not using the same classification scheme, every year, which wouldn't let us compare. So it's considerations like that you really need to think about if you're using kernel density, or really if you're comparing data year over year. And then this one is just adding in a few other classes and visualizing this kernel density all at once for all 8 years worth of data. And kernel density, it's a good visualization. It gives you a good place to start to see where the most points are occurring. And I think that's about it. I mean, it's a good starting point because it helps you make a little bit of sense from some basic point data. The next thing we can do, right, is we can actually take a look at some spatial statistics, right? So the kernel density, right, there's no statistics here. It's basically saying, all right, if you have a lot of points close together right here, it's going to be a darker color because there's a lot of points close together. There's nothing statistically significant about it. It's just, yeah, there's a lot of points close together. So it makes a darker color on the map. With spatial statistics, right, it uses actual spatial statistics equations, much like regular statistic equations, to determine levels of confidence via p-values, to give you basically statistically significant ideas of or statistically significant relevance if there is clustering or not clustering of values in certain locations. Now, if you're doing this with point values, right, data has to be aggregated. So you can't use individual points. You have to have a specific polygon or point with an attribute field that has a data value. So in this case, I used hexagons. Sorry, I just had to pause it for a second. I think my baby started crying. Anyway, we're back now. So we used hexagons to aggregate the data. So basically, we created a grid of hexagons across this map and then counted up how many points fell in each hexagon, and then that hexagon got a numerical value of how many points fell in that hexagon. And we used hexagons because they are one of only 3 shapes that fully tessellate. So basically, a square, a triangle, and a hexagon can fully cover a 2-dimensional plane without any gaps in between the individual shapes, which is what fully tessellate means. And hexagons give you a better, once the data's aggregated up to the hexagonal grid, the hexagon or the hexagonal grid gives you a better approximation of the underlying pattern of the points, right? It doesn't distort the actual pattern of the points as much as a square or triangular grid. And when you're visualizing the data via the hexagons, because of the pattern of the hexagons, you're not inclined to see the actual pattern of the grid as much as you are with the square grid, because with the square grid you see the actual grid, right? The vertical and horizontal lines of the squares that make up the grid. You don't see that as much with the hexagons. So that's why I used hexagons. And so after we aggregated the data and ran the spatial statistics models, we got back these results that indicated these locations of spatial clustering with these different significance values. So basically, we got z-scores, right? And those z-scores have corresponding p-values, right? And so just like normal statistics, the darker the red in the hexagon indicates a very, very, very low p-value. So basically, the darkest red have p-values that are less than 0.01, which indicates a greater than 99% chance that this pattern is not due to random chance, right? So there's something, we can be highly confident that there's something driving this specific pattern of calls for service or a specific pattern of points in these locations. And, with our knowledge of the city, we can actually understand why there are specific calls for service at these locations, right? So the majority of these dark red locations are nursing homes, right? With the exception of the fire division and the senior center, that's a nursing home. That's a nursing home. These are nursing home and assisted living. This is a nursing home, and that was actually Section 8 housing, another nursing home. And then you see some of these other ones, why they might be getting calls for service. So we begin to see the pattern of why exactly there were specific calls for service to these locations. So it's the data now backing up anecdotal evidence that was given to us by people in the city and firefighters. And this is just a specific Pareto chart and another chart kind of backing up that story. So basically now, we can use some other tools to help us highlight the shift year over year in the trend and the directional trend of those calls. So there's mean center, which basically shows just like the arithmetic mean, right, which shows the middle number, the middle location of a numerical data set. The mean center in a spatial data set shows the middle location of all of the data points. And then directional distribution is a shape. It's normally an ellipse that encompasses roughly one standard deviation, so roughly 65 to 70% of the data, and it shows you which way and how far or how wide or how dispersed that data is. So if you have a very large ellipse, the data is very dispersed, right? But if you have a very small ellipse, the data is very centralized, and it can show you which way data points are moving over time. And this can really highlight shifts in the background data, because we can remove all of these drivers, right? So if we remove these top 5 locations that call, we can really get an understanding of where kind of the background noise or the background calls for servers are coming from and where they're shifting over time. So basically we can see this is from 2007, right? So April 2007 to April 2008 is the blue circle. That's our directional distribution. So our ellipse that encompasses roughly one standard deviation of data. And then the blue is the mean center, right? And so as we progress, now you see that mean center has shifted to the southwest, and the directional distribution ellipse has actually elongated slightly to the southwest as well. Now if you look now in 2009, 2010, it's shifted back slightly, and if we go to 2011, pretty similar. Now 2012, it really shifts pretty far. 2013, 14, and 15. And so when you look at them all together, you begin to see a pattern or a trend over time. So you see the mean centers are shifting to the southwest. And again, this is in the background data, because if you included these main drivers, you wouldn't see any change at all, because they're the main drivers. But we're interested in the background information, the background calls for service. And then if you look at the directional distribution, it's really interesting because the ellipse is moving. The ellipse is changing, right? It's expanding to the south and west. But up here to the north and east, it's really not changing that much at all, right? So the boundary of the ellipse is staying fairly constant up here, meaning there's really no more calls expanding or coming in up this way, but because the ellipse is expanding to the south and into the west, there's more calls coming in down here, and the ellipse, because it has to cover, one standard deviation worth of data, it has to expand to cover those additional calls. So it shows you over time how the calls are expanding. So now that's showing you kind of where the calls are expanding, in which way they're expanding, and maybe why they're expanding that way, which is kind of this map of vacant zoning lands. So now we want to touch a little bit about estimating travel time from different locations around the city. So from the current fire station and maybe from proposed fire stations. And this gets into a little bit of network analysis and then some new methods for modeling drive time. So network analysis, again, we didn't really touch on it that much because it's a little bit more of an advanced topic, which hopefully if you're interested in, you'll read a little bit more about it. Or maybe you'll take some additional GIS classes, or you'll further your career in GIS if you're interested in it. But basically, network analysis is very simple. So it estimates, how far you can get, or how far you can travel along a road in a given amount of time. So basically, if your road is 1 mile long, the speed limit's 60 miles an hour, you could travel along that road in roughly 1 minute. So that's essentially the really rough basis of network analysis. And when you create a really rough network analysis model for the city, we tried to factor in some streetlight and stop sign variables, but basically you get this model. So the dark blue is everywhere you could get in 2 minutes or less, and then 2 to 3 minutes, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and then greater than 7 minutes. So it gives you an estimate, and really that's what it is. It's an estimate of how far a fire truck could go in a given amount of time. But it would be really interesting if you could model this or compare this to real world data. And you can, because you can use something called interpolation. And I'm sure you've all seen interpolation if you've looked at a weather map, because basically all it does is it creates this continuous surface from real observations. So basically with a weather map, you have weather stations around the state, around the county, around the city that observe temperature, and then the weather map creates this gradient. It interpolates, or it estimates a value in between observed values to create this gradient. And we can do that based on all of the 15,000 calls for service we had over 8 years, because each one of those calls for service had a start time and an end time. So it had a time the engine left the station, and it had a time they got on scene. So it gives you a rough idea of how long it took them to get there. And so this is the basic interpolation model of that data. So it looks kind of rough, right? It looks splotchy. It looks, right, you see some really random, like, this is 7 minutes, but it's surrounded by 5 minutes, and it's surrounded by 4 minutes, so that doesn't make a whole lot of sense. Same thing here, it's surrounded by, it says it takes 6 minutes, but it's only, half mile from a fire station. So again, that seems kind of odd. And the reason it's odd is because there are these, there's this variability in travel times, right? And so these next couple of maps highlight the variability in the extent of calls for service with these travel times. So this map here is calls for service with travel times of less than 1 minute, right? And I can tell you this is impossible, right? The fire station's here. This is at least 2 miles, 2.5 miles away. That's impossible, right? Same thing here. It's impossible to get from here to here in 2 minutes, right? Same thing here, right? So the fire station is right here, and this is 1 block away, 500 feet at the most. It shouldn't take 10 to 15 minutes to get there. Same thing, right? This is 2 blocks away, and it shouldn't take 15 to 30 minutes. And this one shouldn't take, this is 1.25 miles, 1.5 miles, and it shouldn't take 30 minutes, right? So this travel time variability, right, because of, poor data, maybe somebody recorded the time wrong, it creates these outliers. It creates these travel time outliers. And basically, it's this combination of a numerical outlier and a spatial outlier. So this numerical outlier is really just a number that's different, right, from other numbers around it. A spatial outlier is a location, right, that's very different. It's very far away from other data points that it's very similar to, right? And these travel time outliers is this combination of the two, right? So it's a value that's very different from the surrounding values. So we can basically do a couple things to remove these travel time outliers. So the first thing we can do is take these run locations, and we can shift them, and we can integrate these run locations so they're on top of each other. So all the red points on the map are the actual original run locations, and so we can use the collect events tool to combine these points within 100 feet of each other into a single location. So you have 9 points here, for instance, and now you shift those points so they're all in the same location, but you still have 9 points stacked on top of each other. And then after you do that, you can average all of the values at that location. So if you have all of these values in their travel times for these points at the location, so 2 minutes, 3 minutes, 3 minutes, 9 minutes, which doesn't seem right because it's very different from the rest of the points at this location. If you shift those and collect them and then average those travel times, it's 3 minutes, which seems very relevant, very similar to the rest of the points. You get rid of this 9. And when you look at the histogram prior to integrating and averaging, right, you see these high values, 20 minutes, 30 minutes, 40 minutes. But after the integration and averaging, the highest you have is 15. So you do away with those really extreme values, but you're still left with some high values in the 10 to 15 minute range, which are still outliers. So we can use some additional spatial statistics to deal with those outliers. And they fall into 2 categories. So basically, we have high values, right, that are surrounded by low values. So here, 14 minutes is surrounded by other values that are much, much lower. So that's a high travel time surrounded by low values. So it's a high outlier. Or 5 minutes surrounded by low travel times, or 4 minutes surrounded by 1 and 2 minute travel times. And out here, we have low travel times surrounded by much higher travel times. So 0.2 minutes, right? So it most likely surrounded by travel times that are 5, 6, 7 minutes. Same thing, 3 minutes. That's probably surrounded by 5-minute travel time. So we can take that additional step to remove those outliers. So after we do all of that, we can rerun the interpolation, and it's much, much, much smoother, right? So it's, we lose all of these random points in there. We still have some in here, but maybe that's just because it takes longer to get back into this area. And when we compare the interpolation to the network analysis, it looks like our dark blue is actually much smaller. So it takes longer to get into this area, but also they can get out to this area quicker. So it kind of stretches out this middle area. So it would be great if we could actually create a model based on this real world data, not this hypothetical, so we could move this fire station around and see what the travel times would be like from different parts of the city. And we can do that using these distance bands. So we can create quarter-mile distance bands using network analysis. Basically just, create these bands of a quarter mile along the road, and then we can spatially join each one of these points to a distance band. And when we do that, we see that as distance increases, right, 1 mile, 2 mile, 3 mile, 4 mile, 5 mile, right, and that corresponds to these distance bands, so does our travel time, which makes sense, right? You're further away, it takes you longer to get there. Nothing too crazy there. But because now we have this relationship, we can create a linear regression model to predict what the travel times would be like at each distance band. And it's a pretty good model. So our R squared is 0.7, which means that 70% of the variability in our travel time is predicted by distance, which is pretty good. The other 30% of the variability comes from something else, right? It could be traffic, construction, weather, some other variable. The p-value is very, very low, which means it's very significant. Our residual plot, they're very close to 0, which is very good. So the model, it's a pretty good fit. So we can apply our modeled values here for each distance band back to that specific distance band. All right, our modeled times. So these orange values are our modeled times. We can apply those back to the distance band, and then we get this regression estimated travel time. And we can compare that with the interpolation, and it looks strikingly similar. And it looks so similar because it's based on the same data. And so now we have some caveats, some assumptions, which is okay. Any modeling you do, you're going to have assumptions. But now we have all of these hypothetical locations where a fire station could exist. We can take this model and we can shift it around to different areas in the city and estimate, right, the percentage of the population that's covered based on these different areas, and essentially rank these different locations based on the number of people covered in 4 minutes, 5 minutes, and 10 minutes, using what we think is the most accurate and realistic travel time model that we could create based on the data that we have. So basically this recaps lots of different techniques for analyzing point data, right? So we've got density visualization using kernel density, where we're taking into account time because if we're comparing kernel density over time, we need to understand the data classification schemes so we can accurately compare over time. So this is a good first step, just to understand where the most points are occurring. We can use spatial clustering and spatial statistics to understand if there is actually any sort of statistically significant pattern to the data, and we can aggregate it to hexagonal bins or hexagonal grids because they're a better method than squares. We can see in which direction spatially the data is trending over time using a directional distribution in our standard deviational ellipse and our mean center, and it can tell us if points are increasing in one direction versus another direction, and then we can use network analysis to model travel time. We can remove our spatial outliers using our additional spatial statistics, and then we can interpolate our travel time so we can estimate values in between known points, and then create our own regression model to optimize the station location. And finally, 4 years after I did this analysis, they're actually breaking ground on the fire station located right here. And that is mainly because this land was owned by the township, and it used to be a township fire station. So they got a good deal on it. But anyway, you can see it's ranked in 4-minute coverage. It's ranked second. 5-minute coverage is ranked third. So it's a pretty good. It's still a very good choice. So this is a great example of analyzing a point data set from start to finish, because it covers lots of different things. It's more along the lines of public service, but if you're going to work in a local public health department, you could certainly use a lot of these techniques, for service delivery type aspects. So just because this work was done for, public safety, certainly doesn't mean it can't be used in other public health areas.